When gas clouds are dragged into a black hole, they are locked away from the universe forever, and they go to their end. In their final moments, these gas particles send out one of the brightest emissions in the universe, a final flash of light. These dives of destruction are too far away to be observed directly, but astronomers have developed a new technique to detect these frantic cries for help. They are using this method to test our knowledge of gravity in the most extreme regions of the universe. In a new study, physicists examine certain properties of light to understand how close one can get to a black hole without much effort to avert a potential catastrophe. This threshold is called the innermost stable circular orbit, or ISCO for short. The researchers also discovered that their method can work with the more sensitive X-ray telescopes that have recently been put into operation. The event horizon of a black hole is the invisible line in the sand across which you can never return. Once anything passes through the event horizon, even light itself, it can no longer return to the universe. The black hole's gravity is just too strong within that region. Outside a black hole, however, everything is just dandy. A particular black hole will have a certain mass, and orbiting the black hole is just like orbiting anything else of identical mass. Gravity is just gravity, and orbits are orbits. Indeed, lots of stuff in the universe finds itself orbiting around black holes. Once these foolhardy adventurers get caught in the black hole's gravitational embrace, they begin the journey toward the end. As material falls toward the black hole, it tends to get squeezed into a razor-thin band known as an accretion disk. That disk spins and spins, with heat, friction, and magnetic and electric forces energizing it, causing the material to glow brightly. In the case of the most massive black holes, the accretion disks around them glow so intensely that they get a new name, active galactic nuclei, capable of outshining millions of individual galaxies. In the accretion disk, individual bits of material rub up against other bits, draining them of rotational energy and driving them ever inward to the gaping maw of the black hole's event horizon. But still, if it weren't for those frictional forces, the material would be able to orbit around the black hole in perpetuity, the same way that the planets can orbit around the sun for billions of years. As you get closer to the black hole's center, though, you reach a certain point where all hopes of stability are dashed against the rocks of gravity. Just outside the black hole, but before reaching the event horizon, the gravitational forces are so extreme that stable orbits become impossible. Once you reach this region, you cannot remain in placid orbit. You have only two choices. If you have rockets or some other source of energy, you can propel yourself away to safety. But if you're a hapless chunk of gas, you're doomed to fall freely toward the waiting dark nightmare below. This boundary, the innermost stable circular orbit, is a firm prediction of Einstein's general theory of relativity, the same theory that predicts the existence of black holes in the first place. Despite the success of general relativity in predicting and explaining phenomena across the universe, and our sure knowledge that black holes are real, we've never been able to verify the existence of the ISCO and whether it conforms to the predictions of general relativity. But the gas that falls to its doom may provide a way for us to verify that existence. A team of astronomers recently published an article in the journal Monthly Notices of the Royal Astronomical Society, which also was uploaded to the preprint journal Arxiv, describing how to take advantage of that dying light to study the ISCO. Their technique relies on an astronomical trick known as reverberation mapping, which takes advantage of the fact that different regions around the black hole light up in different ways. When gas flows from the accretion disk, past the ISCO and into the black hole itself, it becomes so hot that it emits a broad swath of high-energy X-ray radiation. That X-ray light shines in all directions away from the black hole. We can see this emission all the way from Earth, but the details of the accretion disk structure get lost in the blaze of X-ray glory. That same X-ray light also illuminates regions well outside the accretion disk, regions dominated by clumps of cold gas. The cold gas becomes energized by the X-rays and begins to emit its own light in a process called fluorescence. We can detect this emission too, separately from the X-ray blaze emanating from the regions closest to the black hole. It takes time for light to travel outward from the ISCO and outer part of the accretion disk to the cold gas. If we watch carefully, we can observe at first the central regions flare, shortly followed by the reverberation light up of the layers outside the ISCO and the immediately surrounding accretion disk. The timing and details of the reverberated light depend on the structure of the accretion disk, which astronomers have previously used to estimate the mass of black holes. In this most recent study, researchers used sophisticated computer simulations to see how the movement of gas within the ISCO affects the emission of X-rays both nearby and in the outer gas. They found that while we currently don't have the sensitivity to measure the doomed gas, the next generation of X-ray telescopes should be able to, allowing us to confirm the existence of the ICSO and test whether it agrees with the predictions of general relativity in perhaps the most gravitationally extreme regions of the entire universe. The mysteries of the universe are endless, so keep exploring. See you in the next video, and may the stars be with you.